thank you so much. Thanks so much for the organizers and for allowing a hybrid option and being very inclusive. I really appreciate that. So today is sort of a mix of a few things, but this is sort of a general idea that I wanted to share, was just looking at how we can use linear algebraic techniques to have sort of more transparent methods in machine learning. And so I'll mention what exactly I mean by that in a moment. So this contains a collective of work, one of which is by the top three here, as well as the bottom of the three on some work on CUR decomposition. In addition to these collaborators, a lot of the applications and experiments were done by my own research group on the left, as well as several REU groups on the right. And so the methods that I'm going to mention are, they do really well in practice, but they're also relatively easy to kind of jump into and implement. And so I think that that's actually why it's really nice for undergrads even to kind of just try testing them out right away. So I have some motivation and I have way too much motivation, so I won't go through all of it. But probably we've seen lots of these types of things before. So for example, if you're training a neural net to do image classification, it believes that this image here on the left is a panda, but when you add, a very small of what looks like noise to the human eye, suddenly it's convinced, more convinced even, that it's a gibbon, which if you don't know what a gibbon is, I've copied that image below. So some similarities certainly, but we're very, very confident and we're very, very wrong. This is a kind of more famous one where you can add similar type of noise to a pig and all of a sudden he's an airliner. Even rotations can fool neural nets. So a revolver can be rotated to become a mouse trap, a boat house can be rotated to become a guillotine, and so on. For facial recognition, this has also become a serious issue. For example, if you're searching for a face or even just detecting faces, one can evade those detection algorithms by, for example, wearing this pair of glasses. And not only can you evade facial recognition, but actually you can even make yourself look like another person, depending on which kind of shapes you put on the glasses. So this is literally an example of, the Superman Clark Kent situation where just one pair of glasses and suddenly you're not recognizable. This has a lot of really critical issues in social good issues, social justice problems. There's a lot of bias here that is propagated. Many algorithms, right, are trained on data sets that look like a majority group. And so you have lots of errors in minority groups. You see bias propagating in decision outcomes and things like this. So it's a really, I think, critical issue, and it's a very relevant problem to be looking at right now. More on imaging. So this is from a self-driving car. On the left, it's got, it accurately recognizes this as a stop sign, even though it does have some paint and some stickers. However, if you're more strategic with those stickers, you can actually fool this visual recognition system to believe that this stop sign is actually a 45-mile-per-hour speed limit sign. Obviously not a mistake that you want your self-driving car to make. So lots of applications outside of imaging as well. So this is an audio example for a speech-to-text problem, where this first audio recording here recites it was the best of times, it was the worst of times, and the algorithm correctly converts that speech to text. However, if you add a little bit of noise to the waveform, suddenly the speech to text becomes something that is not at all the same. Even though to the human ear and to the visual eye, in this case, the sound is actually pretty close to the same. More examples of kind of speech recognition, and this is Baidu's Deep Speech 2 model and various types of speech. So this is on the y-axis here, we have a word error rate, and we're looking at the error rate for the model, so in this case, the Deep Speech 2 model, and a human error from a particular transcriber pool. And so you notice a couple of things right at the bat. First of all, American accents have much less error. and different types of accent have very different and worse error rates. That's one issue right off the bat. You also notice that even the humans, right, are making more errors, and that's likely due to the transcriber pool being probably drawn from a particular population. Here's sort of a content-based example. So this is a paragraph, an excerpt about the Super Bowl 50. And you feed this as input to the algorithm, then you ask it a question. And in this case, the question is, what is the name of the quarterback who was 38 in Super Bowl 33? And the correct and original prediction is John Elway, which is contained here in this text. The past record was held by John Elway and what his age. However, if you just add extra information, which is totally factually correct, quarterback Jeff Dean had jersey number 37 and Champel. Just with this extra text included, then the prediction becomes something that is incorrect, predicts Jeff Dean. Here's kind of a mix of applications. This is the fun game Pong, right, where the computer is moving two paddles on the left and the right, trying to prevent this ball from passing on to one side off the screen. And so here the ball is moving in this vector direction. And so the correct action the computer should take is to move the paddle down to block the ball. However, if you add a bit of noise, small noise, this is blown up just for visual, you can hardly even detect it to the human eye over here on the right. But with this exact same setup, the computer decides that no action is needed. And so it keeps the paddle there. Similar here on the bottom where we're adding sparse noise, it actually does the opposite action. Let's go with that. So kind of all of these are, examples of either adversarial or accidental examples that can really fool things like neural nets. And so, the big question, of course, is how do we protect from these things happening? So there seems to be sort of two main bodies of work in this direction. One is sort of just keep training, right? So learn these adversaries, train against them, generate the adversarial data that fools the network, and then train against those examples and just repeat. And so this does, of course, improve generalization, but it lacks robustness, right? This kind of seems like the whack-a-mole game where, one thing is popping up, you hit it down, and then something else is going to pop up somewhere else, and that's not clear that will ever end, right? Because the space is so large. And the second approach is defensive distillation. And this kind of uses this idea of a second model that is smooth in adversarial directions. So what this really means is that the second model is trained on the primary model's output probabilities rather than these like thresholded decisions. The good news is it can be applied to any feed-forward neural network. And for a while, people were really excited about this approach because it reduced all of the prior attacks that were designed from 95% success rate of the attack being successful to 0.5%. So it was a very good reduction there. However, recent benchmarks for adversarial attacks have already fooled this approach. For example, Carlini and Wagner from this paper down here in 2017 developed one that it wasn't able to beat. So, okay, well, why do these models fail so easily, right? And I put easily in quotes here because from one standpoint, it's hard to design these adversarial examples. But on the other hand, it's actually quite easy, right? Because the noise that you're adding to say these images is really small, and it's the human eye almost undetectable. And there's lots of space to work with here. So, and one reason why I think this is well, because the data that we're working with is extremely sparse if you consider it in this high dimensional space in which it lives. In images, for example, right? The images that we're actually seeing in this large ambient space make up a very small bit of that space. And so there's then lots of room to kind of nudge these things around and get these bad examples. In addition, the models are often very overconfident, especially considering this large space and the little information they have, relatively speaking. And so Ian Goodfellow, right, the computer scientist, quoted that many of the most important problems still remain open, both in terms of theory and in terms of applications. We do not yet know whether defending against adversarial examples is a theoretically hopeless endeavor, or if an optimal strategy would give the defender an upper ground. On the applied side, no one has yet designed a truly powerful defense algorithm that can resist a wide variety of adversarial example attack algorithms. So where does that leave us? How do we ever trust an input? Or sorry, trust an output? And so this is kind of the approach that I'm going to take in this talk, which is if we could know why a model selects a particular output, then not only does that further our understanding of the method, but then hopefully we can also start to develop trust when we see the results. And so the approaches that I'm going to talk about today, mainly two with many different variations, are going to be linear algebraic, and they're going to allow for this type of transparency where you can really ask, well, why was this input labeled the way it was? So we really want to get away from this sort of black box idea. So the first kind of high level idea, and we have many results on this now in different variations, but at its core is just non-negative matrix factorization. And so this is exactly what the name suggests. I have a large data matrix, say it's users by variables, and I want to factor this into two components, both of which will be very low rank, given that the number of columns in this first factor will be small, and the number of rows in the second factor will be small, and both of their entries will be non-negative. And I'm going to sort of interpret this dimension here as the number of topics. And I'll give an example for concreteness in a moment. So kind of the question might be, okay, well, why non-negativity? Why is this factorization going to be useful for the motivation that I just kind of talked about for a while? And that's kind of demonstrated by this example here. So here we have a bunch of, so this is work by Li and Sung from their kind of big seminal paper in 1999. They took a bunch of images of faces and they performed various factorizations. And so for example, if you just do something like PCA, in this case, you get these sort of eigen faces, if you will, which are shown here in this grid. This is an example of what one looks like. To the human eye, these don't really look at all like faces. However, they are good building blocks to build the face. And you can use these as building blocks to construct all of those faces, and you can do so very accurately. On the other hand, if we require non-negativity, we're learning a very different set of building blocks. And here we're showing them in the same grid. And I know it's a small image, but if you look very closely, you'll see things like noses, eyes, mouths, and things like this, which to the human eye make more sense, right? And so that's exactly why we want that non-negativity, so that we can't just cancel things out in a way that that the images themselves don't make any sense here now, because we're requiring each column of this data matrix, or each face in this case, to be represented as a non-negative linear combination of these dictionary atoms. Then those must be like positive parts of the data matrix, and so they make more sense to the human. So let me just go back here and just give a concrete example of how one interprets such a factorization and what one can do with this. So again, because we're requiring non-negativity in both factors, if you see large entries, they're meaningful all of a sudden. Unlike factorizations that don't require non-negativity, large entries can cancel out and they may or may not have meaning. Here, they're guaranteed to have meaning because everything is restricted to be non-negative. So if I find a large entry here, and this is telling me that this user in this row must have a high association with whatever this topic in this column is. And so then I can go over to that corresponding topic in this variable matrix, and I can say, okay, this is a large entry, so this topic has a large association with whatever this variable is. And going back and forth between these two will allow me to really understand what the factorization is telling you. So just to be extremely concrete, say I have users by movie ratings matrix. So I have movies along the columns and their ratings are in the matrix. And then I do this factorization. Say I see a large entry here corresponding to this user. I can go up and say, okay, this user has a high association with whatever this topic is. Maybe topics here is going to be something like genre, movie genres. And so I can go over into the corresponding genre in this factor matrix, and I look for the large values. And say I see large values corresponding to the movies Titanic, Love Actually, Sleeps in Seattle. This tells me that these are romantic movies if one watches such films. And so this might tell you, okay, this user likes romantic movies, and this gives me a lot of information. And it, of course, tells me that these movies are related to one another in that way. Okay, so mathematically, the problem is quite simple. We're just looking for the best factorization given a particular rank R, which we're choosing. So here we're looking for the tall factor W, which will be D by R, and wide factor H, which is R by N, both of which have non-negative entries. And we're just minimizing, for example, the Frobenius norm error of this factorization. One can then add other regularizers, of course. So you can add like L1 regularizers if you want the topics to be sparse. That makes them more understandable if there's not too many large values. You can add a regularizer for label values. If you're doing something like classification, that would be a semi-supervised version of NMF. So you would have a term here that captures the error and the label information. And that allows you to then do kind of an understandable and explainable classification problem. And we'll call this W matrix the dictionary matrix, and then those dictionary atoms are encoded to the data throughout this coding matrix H. There are many, as I said, kind of different variations that we've studied, one of which is an online NMF problem. And this setting considers data that's streaming in over time. So we have a time series of data. And its goal is to learn the best factorization, usually in something like expectation. And we can also use this to do prediction, which I'll give some examples of in the end. And the idea here is the following. So if we have data, say x1, x2, x3, that's changing over time, then we're going to learn factors W0, H1, W1, H2, and so on as time changes. And in fact, we'll even be doing each of these iteratively. So there's lots of iterations here happening in sort of multiple modes. And if I want to say reconstruct X4 and see how good my reconstruction is, I could of course just multiply these two together and reconstruct X4. Now, if you imagine that I have sort of a window that I'm sliding across, all of these W2 and H3s, they're built upon the previous W1 and H2, right? And so they're kind of, we're iterating through time using the previous factors as approximations. And I can keep doing this to get my reconstruction, but if I slide that window kind of beyond where I have data, I can still do reconstruction based on the current factor I have. But because I don't have that data in real life, that becomes a prediction, right? So that's kind of how we go from a reconstruction to a prediction just by sliding the window into the future. And I'll show some examples of this later on. I'll just quickly say that everything I'm talking about extends to tensor case as well. Non-trivially, just because the linear algebra gets complicated, but they do all hold in an analogous way. So if you have tensor data, all of this works there as well. So here's the diagram. This is for the static case when there's a single X. And so as I hinted at, we can do this iteratively. One can use a Blockhorn descent approach. And so we're iteratively fixing W and solving for H and so on. And so this leads to the most popular static NMF method, which is the multiplicative update method by the same authors I mentioned before. And so it's actually very succinctly expressed as this entry-wise update rule, which again is why I think it's really nice for undergrads to jump into. It's really easy to implement. You can get some interesting results right away. Theoretically speaking, it's known that the error, the Frobenius error with this multiplicative update rule is not increasing, but currently there's no guarantee to convergence to a stationary point. So what happens when we go into this kind of online or streaming world? As I mentioned, we're usually going to look for factors that best represent the data and expectation. So we need some sort of stochastic assumption on the data. And there'll be two that I'll consider here. So one is going to be that the data is IAD streaming, and the other one will be a slight generalization of this. And so this is the goal of this problem. For us, we're going to consider a Markovian model, and I'll explain kind of what motivates that in a second. And the goal here will be, so say I have XT is my data, and it's going to be an irreducible Markov chain with unique stationary metric pi. Then the goal of online NMF is to construct a sequence of W and H pairs such that almost surely we have this convergence here. So just stare at this for a second. We're just saying that the Frobenius error at time step t converges to the best possible, best meaning over all the possible factors, best possible error in expectation, where the expected value is taken with respect to the distribution on the data. So kind of pretty intuitive that we want the best factors in expected value. So what motivated this was work by this group here, Myril and others, who gave a solution to this problem under the assumption of IID data streaming. And so I won't maybe go too much into detail here, but the motivation for this problem is sort of to consider this iterative solution, this iterative scheme here again. There become a lot of technical issues with doing this. And so one needs a surrogate function for the actual empirical loss here. Again, we'll kind of skip over the details there, but if you're interested, I can certainly elaborate later on. And the good news is we don't have to store a whole bunch of data. We're recycling previous found coding matrices, and we can even get away with not having to store any of the history. Instead, we aggregate all of the history in these two matrices here, AT and BT. And so the end method is this simple iterative scheme whose pseudocode, as you see here, is really just 4 lines. And the amount of storage that you need is very small because you only need to store these 4 at a given point in time. So it's pretty feasible in terms of practical considerations. So given this update scheme, this group proved that if your data is IID with distribution pi and WT and HT are the solutions to this scheme above, then you get the following guarantees. You get that the empirical loss and the surrogate that you're using in the algorithm converge to the same constant. This sort of suggests that the algorithm has a chance to be doing what you want it to do. And the good news is that indeed, the gradient of the loss does converge to 0 almost surely. And so this is exactly the guarantee that you want. And so we were starting to look at this, and we had a bunch of applications that we wanted to use this online NMF for, but it was really challenging for us to justify in these applications why the data would be IID. So we were, for example, this was March 2020, we were looking at COVID data and wanting to do COVID predictions, and there was no reason whatsoever for us to believe that case counts were independent from one day to the next. We were also sampling very large networks, and we wanted to do a random walk, so we didn't have to jump all around the network. And so that also lost the independence assumption. But all of the ones that we were looking at seemed very reasonable to assume a Markovian assumption on them. And so we wanted to see if we could extend this result to the Markovian setting. So that's what we were able to do. And so we proved, so the algorithm is exactly the same. We did not change the algorithm at all. All we changed was the assumptions. We removed the independence requirement and allowed the data to be Markovian, and we kept the same method and we got the same guarantees. So we say that the empirical loss and the surrogate converge in expectation to the same constant. We get that the empirical loss and the surrogate converge to 0 almost surely, and again, we get that the gradient also converges to 0 almost surely. So some good theoretical guarantees that we can also use this exact same algorithm for Markovian data, which is many of the applications that I'll show in a second. So this hopefully is going to hint at, and when I show the applications, hopefully it'll become more concrete, a method that we can use for doing many machine learning tasks, but where, because we're doing something with a non-negative factorization, it'll also be able to see why the outcomes are what they are. So a second linear algebraic approach, besides non-negative factorization, would be something like a CUR decomposition. So just to remind you, in the matrix case, if I have a D by D matrix A, I create a D by K column submatrix called C, an S by D row submatrix called A, and then I look at the intersection, which in this diagram here would be literally the purple with the overlap of the red and blue, and call that U. And then the kind of big theorem, of course, is that if the rank of U and A are the same, then this gives you an actual CUR decomposition. So you can actually write A in this way. And this to me has a similar flavor as NMF, because if we're using these matrices here, CU and R, to describe our data and give us some outcome, this is already a component of the data. So if we know something about our actual data matrix, then we should also be able to understand what C, R, and U are sort of representing. So I feel like it has that same sort of flavor. And so the question that we asked was, can this matrix CUR decomposition be generalized to tensor case? And so this is work with Longzhu Wang, as I mentioned on the first slide. And the motivation here is sort of to say, okay, well, a matrix is a tensor, so let's write the CUR decomposition in a really annoying way, but just using a mode-wise decomposition. And this sort of suggests a hint as to how to generalize this to the tensor setting, but it's not an obvious answer. And so we have two Main theorems, I'll go through them very quickly because I have a drawing that actually does a much better job. But there's two factorizations that we defined and developed. One is what we call a Chidori CUR, and I'm going to skip all of the juice because the picture will do a much better job of explaining the details. But the punchline here is that you get a similar CUR factorization for the tensor, where the components are also going to be subtensors, just like in the matrix case. And you also get similar guarantees about the ranks. The second one is a fiber CUR. You get the same sort of guarantees. It's going to look a little bit different. And again, I'm just going to jump right to the drawings. I think that does a better job. So this Chidori CUR decomposition has this sort of picture here. So this is looking at a 3-mode tensor as this sort of black outlined object here. And the indices are these intervals here. So just like choosing which row indices and column indices in matrix case here, we're choosing these indices here. Then the matrix, say C1, so column version here is obtained by unfolding this red subtensor. C2 is obtained by unfolding this green subtensor here, and C3 the yellow, and then these dotted lines give you the core sort of R subtensor there. And so Longju was presenting this to an audience that contained Dustin Mixon, and he said, oh, this looks like the Chidori game. So this is a picture of the Chidori game, and so that's the name Chidori CUR. The fiber CUR is a similar idea, but there's a little bit more flexibility in how you're picking the indices. So there doesn't necessarily need to be this nice overlap for your core tensor R. So here, the lines correspond to the rows of C2, and the red indices within them correspond to the rows of U2, and so on. And then this core subtensor R need not intersect all of them. So it's a little bit more flexible there. And so these results also allow for other applications, which I will show for the rest of the talk. Okay, so the first application is work that I've been involved in for a while now, and this is on Lyme disease data. So Lyme disease is a vector-borne disease. It's typically transmitted by tick or insect bite or blood-to-blood contact. Its symptoms mimic those of other diseases and are quite often misdiagnosed as MS, ALS, Parkinson's, fibromyalgia. And many of these can be chronic, especially if not treated and diagnosed correctly right away. The CDC estimates 300,000 new diagnoses each year, and there's plenty of studies to suggest this is a grandiose underestimate. The disease in general is poorly understood, poorly funded, poorly diagnosed, and poorly treated. And so the CEO that I've been working with here, looked at this and said, well, this is just prime for data-driven research. And so she launched this initiative called My Lyme Data. And we have a very large survey result now. We've been doing a lot of work with this. So one of the things that they ask in the survey, so this is of about 14,000 patients now, and they ask many, many questions about diagnosis, about treatment, and also about symptoms. So this is a result where we're just looking at the answers from the symptom questions. And so this is a list of symptoms here, and then the patient rates how severe that symptom is to them at that current point in time. And so here I just focus on the rightmost plot. These are just variations of the method. And what I've done here is a 5-rank non-negative matrix factorization on this symptom data. And I've just grouped the symptoms together so it's a little bit easier to see the topics. So for example, this first topic here has large values, so dark orange is large here, corresponding to these first 3 symptoms. Topic 2, topic 3, topic 4, topic 5. And so we presented this to the board at LymeDisease.org, consisting of mostly Lyme physicians, as well as policymakers and some other folks. And they actually got pretty excited about a couple of things once we sort of explained what they were looking at. One of which was this actual topic here, this third topic. If you look at the symptoms, this topic suggests that there's a group of patients that correspond to memory loss, twitching, sleep impairment, and cognitive impairment. And this really screamed to them that there's a neurologic manifestation here. And that's actually something we've seen in other studies, more clinical studies, that show that Lyme disease seems to manifest in different ways, one of which is cardiac, one of which is neurologic, one of which is more physiologic. And so this suggests that this group of patients actually might be seeing exactly that neurologic manifestation. If we can identify those patients, then we can treat them differently, study their illness separately, and so on. And so that was pretty exciting. The other thing that they noticed was this bullseye rash question, which used to be the key to diagnosing Lyme disease. You wouldn't even get treated by a physician unless you presented with a bullseye rash, like a rash that looks like a target. But lately, more studies have shown that actually it's more like 25 to 30% of people present with a bullseye rash, nothing like what they had originally thought, which was close to 100%. And the fact that this bullseye rash is one of the few topics that really, one of the few symptoms that doesn't really showcase itself very strongly anywhere, sort of suggests that that may really not be key to any type of diagnosis. So that was something else that we wanted to look into further. Here's an example on images. So here we're using online NMF, where the online piece is walking through the patches we sample in the image. And we're learning the building blocks here shown on the right, and we're using them to do reconstruction. So this is a version of compression. I'm not at all suggesting that ONMF is the way to go for compression, but it can be done if there's a reason that you need to sort of have building blocks that are more human interpretable. So even with these visually appealing building blocks that look like the brushstrokes, right, of the painting, you still get pretty reasonable reconstruction. Here's a really good application that I like. This is for image classification and co-segmentation. And so here we're doing classification with NMF, so a semi-supervised version. As I said, you add that regularizer term for the label error. And then what we do is we not only classify the objects as the images as belonging to a set of classes, for example, the cow class, dog, car, and bicycle, but then we actually go back and we look at that topic and we see which pixels actually corresponded to that label. So why, in other words, why was the image labeled the way that it was? And so in this first row here, you're seeing the images themselves, cow, dog, car, and bike image. And then this middle row is the one that I'll concentrate on. We're highlighting with color the pixel image, the pixels in the image that most correspond with the label. So what are we looking at here? So in this, oh, question? No. Are you still there? Okay, strange. So in this example here, we see that these images were indeed correctly classified as cows, and the pixels that most corresponded to the label were indeed the pixels that contained the cow, right? So here you see these pixels were cows, there was a cow there, and so on. And this is great news, right? Because it tells us that the reason that the label was applied was not because of maybe grass in the background or a mountain or anything like this, it was because of the actual animal. And this, I think, will build trust when the human can look at this and see exactly why the label was given as it was. The same with the dog. We tend to see the face of the dog being very important. The car, we tend to see things like headlights and wheels being very important for that car label. And bicycle, kind of similar. We see handlebars, wheels, and so forth. And last time I gave this talk, somebody pointed out that the reflection of the wheels actually wasn't highlighted, which I think is actually quite fascinating. So it's somehow learning the difference in the actual bike versus kind of the artifacts from the bike. So this is, I think, is getting at that, you know, if we had done this pig version at the very beginning, and if it did accidentally classify the pig as an airliner, we'd be able to at least go back and look at which pixels were really the reason why that was done. And so I think that this is helpful in terms of getting towards that explainability. So I only want to go for like maybe one more minute, so I'll just quickly end with a prediction example. So again, I said a lot of this work started in 2020, and so we were looking at COVID cases, and we applied NMF, online NMF to COVID data, both confirmed cases, deaths, and recovered cases. And for that, we had 6 different countries at the time. And so what you're looking at here are the atoms, the dictionary atoms, the building blocks for those various time series. And then we can use those building blocks, as I said, by sliding a window, viewing a reconstruction, and when we're into the future, that reconstruction becomes a prediction. And so here we're showing, using this technique, we're showing the predicted values against the actual values. So this is for the 6 different countries, this is for confirmed cases. And so we're graphing in blue the actual cases, and in red are predicted values. And so you see that actually our method does a pretty good job at making these predictions. The one it really struggles with over here is China. And I think this highlights kind of an important piece to this algorithm. What happened here was China sort of didn't report cases for a while, and then there was a huge spike, and then it sort of went down again. And so because of this decrease in the large spike, our algorithm suddenly expected to see that pattern, right? So you're seeing these kind of patterns appear right here on the right in the building blocks. And so our method really started predicting this kind of unusual behavior for a while. It took a while for it to sort of erase that from its memory. And so I'd like to, in the future, kind of extend this beyond this very localized prediction, right? We're using very localized patterns to make the prediction. And we can maybe combine that with something more global, like an SIR model. I think that would be really interesting. I think that goes into other applications as well. So I'm going to skip. We've also done some work with EEG, but for the sake of time, I think I will just end with some CUR application, which is a robust CUR method for doing something, for example, like detecting background and foreground. And we actually show that we can be quite fast compared to things like robust PCA. And again, because you're using CUR, your building blocks are actual pieces of the data. And so you're sort of, even though you're doing a machine learning task, you also don't have to sacrifice by using a black box method. You can sort of go inside and understand actually what's happening. We have similar results for facial recognition problems, but I think I will end there and save a couple of minutes for questions. So thank you so much.
Thank you. Questions?